Good day, viewers all over the world. You are welcome to Toydel online class. Today we want to look at exponential form of a complex number. And when I introduce complex number, so we started with the standard form of a complex number. We said that z, which is defined as a complex number, is given as a plus ib, where a is the real part and b is the imaginary part. So this I is given as square root of minus 1, and I squared is equal to minus 1. And that has been the standard. So when we look at addition, subtraction, multiplication, and division of a complex number, so we've talked about conjugates of a complex number. Then from this standard form, we were able to derive the polar form of a complex number. So the polar form of a complex number, z is equal to r, where r is called the modulus. R is given as square root of a squared plus b squared. Then where theta is called the argument, that is theta is called the argument, arg of z, and it's given as arctan b all over a. So we have done this, these two forms of complex number. So today we want to look at how we can actually transform from polar form of a complex number to the exponential form. We recall, let's recall that if we have exponential x, the power series expansion of this is given as 1 plus x squared over 2 factorial plus x cubed all over 3 factorial plus x squared all over 4 factorial plus dot dot dot. If you have exponential x, this is the power series expansion of that. Then if you have sine x, the power series expansion of sine x is given as x minus x cubed all over 3 factorial plus x raised to power 5 all over 5 factorial minus dot dot dot. We also know that the power series expansion of cos x is 1 minus x squared all over 2 factorial plus x squared all over 4 factorial minus x raised to power 6 all over 6 factorial plus dot dot dot. So there is something that is common here. If we had sine x plus cos x, we are going to get exponential x. That is the addition of these two, 1 plus x, then minus x squared. If there's a way we rewrite this. So this is the power series expansion of what we have on the board. But if we decide to replace x by I theta, I theta, if we replace x by I theta, what will happen? We are going to get exponential I theta to be equal to 1 plus I theta. Wherever we see x, we change it to I theta. Then this will be plus I theta squared all over 2 factorial plus I, this is I all squared. Then here, this one will give us I theta cube all over 3 factorial plus I theta quarts all over 4 factorial plus in that order. In that order. So in that order. So if we expand this, we are going to get 1 plus I theta. I square is minus 1. So we have minus theta squared all over 2 factorial. Of course, here we have I raised by 3 will be I squared times I. I squared is minus 1. So I'm going to have minus I cube theta all over 3 factorial. Here we are going to have plus because I squared is minus 1. So I raised by 4 will be 1. So we have plus. We are going to have plus theta raised by 4 all over 4 factorial plus in that order. That's what we are going to get. Then if we are going to have sine theta. Sine theta will be sine I theta. Sine I theta will be where I have x. I'm going to have I theta minus I theta all cube all over 3 factorial plus I theta raised to power 5 all over, that will be all over 5 factorial minus dot dot dot. If we do the same thing to cos, Instead of theta, x, I'm going to have I theta, cos I theta. Cos I theta, in this case now, cos I theta will give me I theta all squared all over 2 factorial. That's what we are going to get. Then here I'm going to have I theta, everything raised by 4 all over 4 factorial. Then here I'm going to have I theta, everything raised by 6 all over 6 factorial, and in that order. So if we expand this, you realize that exponential I theta is going to give me what I have here. This is what we get in that order. This is what we are going to get, exponential I theta. Then if I expand this, if I express cos I theta will give me 1. I squared is equal to -1. I squared -1 -1 so I'll get plus theta squared all over 2 factorial. Then I raised to power 4. That's I squared times I squared minus, that's the plus. I have plus theta raised to power 4 all over 6 factorial. Here, I will have I raised to power 4 multiplied by I raised to power 2. That will give me I raised to power 6. This is 1 times -1. So I'm going to get minus this. This will be plus theta raised to power 6 all over 6 factorial plus in that order. That's what I'm going to get. But if I expand this sine I theta now, sine I theta, this will give me, I can bring out I outside. Then I'll be left with theta here. If I bring out I here, I raised to power 3. So once I bring out 1, I'm going to have I squared. I squared is -1. So I'm going to get plus I squared all over 2 factorial, 3 factorial here. That's what I'm going to get here. So that's what I'm going to get there. So I will have I after, I will have all over 3 factorial. Then here, if I bring out I squared, I is outside. I have I raised to power 4. I raised to power 4 will be plus, so I will have plus theta raised to power 5 all over 5 factorial plus in that order. So if we compare this now, if we compare what we have here and what I have here, the combination of these two is going to give me e raised to power exponential I theta. Look at exponential I theta can be equal to cos theta, cos I theta plus sine I theta. So if we do that, that's what I'm going to get. So no, here will be sine theta. So sine theta will give me this. Then cos theta will give me this. So in that case, if we compare these two now, addition of these two, sine theta plus cos theta is going to give me what I have here. So invariably, exponential I theta is going to give me cos theta plus sine theta plus I, because there is I here. It's going to give me plus I sine theta. So I can rewrite everything in this form now. What I'm trying to say in essence is that I can rewrite everything in form of, that is, I will say that exponential I theta is equal to, is going to give me, so here I will have, it's going to give me, exponential I theta will give me cos theta plus I sine theta. If I look at that critically, that's what I'm going to get. So exponential I theta will give me what I have there. Then we know that from the polar form of complex number, we are given this as r into bracket cos theta plus I sine theta. This is the polar form. So if I take this, and of course I know that everything here is cos I theta. So my z can be equal to r e I theta. So that's what z will give me. So therefore, the three forms of a complex number is that when z can be equal to a plus ib, this is the standard form. This is the standard form of a complex number. Then we also have z to be equal to r into bracket cos theta plus I sine theta. This is the polar form. This is the polar form of a complex number. Now, the exponential form z can be equal to r into bracket e I theta. This represents the exponential form of a complex number. So if you are given any complex number, you can actually rewrite. You can move from polar to standard, standard to exponential, and if you are given exponential, vice versa, you can move from exponential to polar, then polar to standard form. So these are three forms of complex number that we can have. So, but in this exponential form now, our argument is in form of pi, is in form of radian, pi radian. So we should note. But here is theta, is normal angle theta, which is in degrees. So I'll just take one example on this. The example I gave the last time, where we are asked to find example in polar in exponential form. Let's say example one. We have to express z is equal to 3 plus 5i in, let me just repeat the question, in polar, let's say in polar and exponential form. In polar and in exponential form. Of course, just to use this to revise the polar form. Z is equal to 3 plus 5i. So in this case now, we can which is same thing as z is equal to a plus ib. So we can say a is equal to 3 and b is equal to 5. So r, which is the modulus, is given as square root of a squared plus b squared, and that will give us square root of, in this case now a is 3, we have 3 squared plus 5 squared, then this will equal to square root of 9 plus 25, then r will give us square root of 34. That is what r will give us. Then if we find the square root of 34, we are going to have it to be 5.83. So this is the modulus of the question. Then we go ahead and find theta in degrees. So theta is same thing as arctan b all over a. This is the argument. So in this case now, we are going to have this to be arctan 5 all over 3. Then this will give us arctan 1.5 all over 3 is 1.4. So if you find the arctan of 1.4 in degrees, we are going to get that. We are going to get it to be equal to 54.5 degrees. So that will be, we have gotten, this is the argument. The modulus r is what? 5.83. So what will now be the polar form? We have to express the standard form in polar and exponential. So the polar form z by formula is given as r into bracket cos theta plus I sin theta. We have done this in the last class. Then r, which is 5.83 into bracket cos 54.5 degrees plus I sin 54.5 degrees. So here I'm going to have 5.83 into bracket cos 54.5 is going to give us 0.5807 plus, then sin 55 will give us 0.8141 I. That's what we are going to get. So if we open up, if we expand this to multiply this, we are going to get 3.386 plus, when we expand that, we have 4.746 I. So this will represent the polar. This will represent the polar form of the given question. So this is the polar form from the standard form that we are given. So this will represent the polar form. Then, but we have to find the polar and the exponential form. So how do we get the exponential form? Of course, we are going to convert theta to pi radian. So we convert it to radian. If we want to do that, that will be pi all over 180. So convert this to radian. That is this what I'm saying. We have gotten the polar form. So we want to find the exponential form now. So to be able to find the exponential form, this is what we do. We just say theta will now be 54.5 all over 180 pi in radian. So as I said earlier on, in exponential, the value of theta is not in degree, it's in radian. Then of course I can rewrite this. If I don't want to decimal, I can say 2 multiplied by 54. This will give me 109. This can be equal to 109 by 360 pi. This is pi, we can call it pi right. So that's what we are going to get. And of course, what is z in exponential? Z in the exponential is r e I theta. We know the value of r. So r is 5.83 exponential. Then the value of this is 109 all over 360 pi I. That's what you get. Then z will now be equal to 5.83 exponential. If we find this now, at the end of the day, we are going to have it to be 0.303i. So this is the exponential form of that given question. So we should note that we can actually convert a standard a complex number in the standard form. Most of the time, will be given in standard form. We can convert from standard form to polar form. In case of polar form now, the modulus is still the same, but the argument, which is the theta, is in degrees. But if we are to ask to convert it to exponential form, then we convert that argument back to, we convert it from degree to radian. That is how we divide the value by 180 pi. So that's how to convert it. Then from this given question now, we have been able to convert that standard form to exponential form. This will be the exponential form of the complex number. So it is necessary, and it is important and necessary to be able to convert that to exponential form. So we should take note that it is important and it is necessary to be able to convert from logmatic form to exponential form. So now let's look at the logmatic from polar form to exponential form. So let's look at the logarithm, the logarithm of a complex number. How do we find the logarithm of a complex number? Of course, it's very simple and straightforward. So we know, what do we know? We know that exponential I theta is same thing as cos theta plus I sin theta. That is, if you look at the power series expansion of these two, it's the same. Power series expansion of exponential I theta is going to give us the power series expansion of cos theta plus I sin theta. So that is a known fact. So if this is the case, then if we decide to replace theta by minus theta, then we get exponential minus I theta is going to give us cos theta minus I sin theta. That's what we are going to get. If we replace that, that's what we are going to get. So if that is the case, then where are we driving at? So so that so in this case now, so that our z in polar form is what? R into bracket cos theta plus I sin theta. That's the z. So in polar form. So in exponential form, z is equal to R E I theta. That's the exponential form of z, the complex number. Then if we take the in simply means natural logarithm. If we take the in of both sides, in z is going to give us n into bracket R E exponential I theta. So another n simply means log e is a natural logarithm. This is the meaning of in z, log z exponential. So in of this, then at this case we can have in R, plus this product, we can separate it as in, this will give us in exponential I theta. And of course, if we have in and exponential, it's cancelled out. That is, this simply means we have in R plus in simply means log e base e I theta. If of course, I theta can come down so that we have in R plus I theta log e base e. If you have a log and if the log and the base is the same, it is 1. So therefore, in z will now be equal to in R plus I theta. So that's what you are going to get. So this is the logarithm of a complex number when it's in exponential. If you have in z, it's going to be, if you have z to be R I cos theta, the logarithm of this complex number is going to give us this. So in simply means log e is a natural logarithm. So that's what you get. Then, so that is what you are going to get. But if we now have z to be equal to R exponential minus I theta, the only difference is that where you have plus it will just be minus. Then in z, if you find the logarithm of this, is going to give us in R minus I theta. Want to follow the process. So please let's note, because our exponential form, our theta is in radian. So we use the natural logarithm. In simply means log e. So this is the logarithm of a complex number. Once you convert the complex number to exponential form, then this is how to write the logarithm. So I would love to stop here because of our time, but we should note that, as I've said in the last class, you can also find the multiplication and division of complex number in polar form. We have done that of standard form. We have done addition, subtraction, multiplication, and division. So we can also derive the multiplication and division of a complex number in polar form. Then the generalization of that is going to give us what is called the De Moivre's theorem. So in our next class, I'm going to talk about the De Moivre's theorem, which is a very important theorem in complex analysis. So I would love to stop here because of our time. So in our next class, we are going to be, so we know all the derivation of a complex number now. So we continue from there. We are going to continue from there in our next class. So I'm going to talk about the generalization of the polar form of a complex number when we have addition and division and multiplication of complex number in polar form. We also talked about more on exponential form. Then we are going to derive the Moivre's theorem. Thank you.